In the previous video, we introduced the three different types of planar rigid body motion. In this video, we're going to try to characterize two of these three motions. The two that we want to look at is rigid body translation and fixed axis rotation. So let's start with translation. Just to point out a few things here, so we have a fixed reference frame. Okay, so this reference frame is not moving. And we have our random object in yellow, and two particles A and B within that object. We want to find its velocity and acceleration. As you can see, I've drawn some position vectors. These are called RA and RB. These are position vectors of A and B with respect to a fixed reference frame. So we call these RA and RB. We could also call them RA with respect to, if we want to call this O, then this could also be known as RA with respect to O. Okay, so these are what we call position vectors. Note that we also defined a third position vector. This is called the relative position vector, and this is R of B with respect to A. So we call this a relative position vector. And it goes from A to B, and please take note of this nomenclature over here. So again, we can say this out loud as RB with respect to A, or you can think of it as R of A going to B. Okay, so let's consider a single point. Let's consider point B. We can express the position of point B as the vector addition of the position vector RA plus R of B with respect to A. So if you remember from high school, adding up two vectors, you can get a third vector. So adding RA plus R of B with respect to A will give you RB. Okay, so we've characterized the position of point B. What about the velocity? Recall that the velocity is the time rate of change of the position vector. So what we can do, if we want the velocity of point B, is take the time rate of change of the position vector, which we have RA plus R of B with respect to A. Now recall that differentiation is a linear operator, so we can just distribute it within the bracket. So we have dRA divided by dt plus dR of B with respect to A divided by dt. So as you can see here, this is just the time rate of change of the position vector RA. So that's just the velocity of point B. Okay, so what we're saying is that the velocity of point A rather. So what we're saying so far is that the velocity of point B is equal to the velocity of point A plus this dR of B with respect to A by dt term. Now what is this? Recall that a vector is both it characterizes a magnitude and a direction. In the previous video, we said that translation, or during rigid body translation, a straight line maintains its orientation. Thus, in terms of the orientation, there is no time rate of change of the vector in terms of its orientation, because as the definition of translation goes, this a straight line between any 2 points, which in our case is r of b with respect to a, it maintains its orientation. So again, a vector has a magnitude and a direction, and we've established that its direction is not changing with time. Now what about its magnitude? Well, recall we're dealing with rigid bodies here. We're not dealing with deformable bodies. So the magnitude of r of b with respect to a is also going to be constant, so its time rate of change is going to be 0. So we just say that this is equal to 0. So we've established a second fact here, is that VB is just equal to VA. Or in other words, all points on the rigid body have the same velocity. Not too bad so far. We can go one step further and look at the acceleration. If we differentiate one more time, we're going to see that the acceleration is also the same at each particle on the rigid body. And this is our characterization of rigid body translation. And this applies to both rectilinear translation and curvilinear translation. Okay, now let's consider fixed axis rotation. We consider an arbitrary object rotating about a fixed axis. So again, the fixed axis in this case is the origin of our xy system. So how can we determine the velocity and acceleration of a given point? And here we're going to consider point P, over here. So recall that for a rotating body, the linear velocity, v, of point P is equal to the time rate of change of the position vector. So we can define a position vector here, r. It's just the time rate of change of that position vector. Without going into the details, because you've probably already seen it, the linear velocity is equal to the angular velocity omega crossed with the position vector. Okay, now I just want to be abundantly clear here. So this, well, there's a few things to point out here. So this position vector here, we could also write it as r of p with respect to O. Okay, so let's make sure that our position vector is oriented in the right direction. Okay, so we are going from O to P. Now this here is the cross product. Okay, so it's not your standard multiplication, it's a cross product. And this is your angular velocity. So angular velocity is the time rate of change of the angular position. Okay, so we can define some angular position, let's call it theta, if we want. So we could say that our angular velocity omega, which you note is a vector, is equal to omega in the k direction. So recall we have these basis vectors here, I hat, j hat, and then k is out in the third dimension. Okay, so we are rotating in the ij plane. So the angular velocity vector is pointing into or out of that plane, depending on the direction of rotation. And this omega is defined as the time rate of change of theta in the k direction. Okay. So this VP is our linear velocity of point P. This is omega here, our angular velocity. And note that the angular velocity does not change throughout the body. It is the same. We have a cross product here, and we want to make sure that our position vector is pointing in the right direction. Okay. So this linear velocity here, we can write it as omega k crossed with r. And note that the linear velocity is going to be perpendicular to the position vector. So this point P, by definition, for fixed axis rotation, it follows a circular path, and the velocity at point P is tangent to that circular path. So what all of this is telling us is that if we know the rate of rotation of the body, we can calculate the velocity of any point on that body. Let's extend this to acceleration. So what we will have to do is differentiate the velocity of point P with respect to time. So the acceleration is the time rate of change of the velocity vector with respect to, the time rate of change of the velocity vector, which we've defined as omega crossed with r. So we'll apply our product rule here. So we have d omega by dt crossed with r plus omega crossed with dr by dt. Okay, so at this point we can simplify a few things. Let's first note this term over here. Okay. This is the time rate of change of the position vector. The time rate of change of the position vector is just the velocity vector v. Now we'll define this here. So this is the time rate of change of the angular velocity vector. So if we think back to our linear counterpart, the time rate of change of the linear velocity is the linear acceleration. So in this case, the time rate of change of the angular velocity, omega, is equal to the angular acceleration. So we define the angular acceleration as alpha, and that is equal to the time rate of change of the angular velocity. And we call this the angular acceleration. Okay, so this leaves us with alpha crossed with r plus omega crossed with v. And just in the previous step, we've already defined v as omega crossed with r. So let's substitute that in. So we have alpha crossed with r plus omega crossed with omega crossed with r. Okay, there's one last simplification that we can do. But to do this, we need to employ a certain identity. So notice here, we have what's called a vector triple product. And we can use this following identity here. So we can say that A crossed with B crossed with C, and all of these being vectors, is equal to A dotted with C, so the dot product of the first and the third vectors multiplied by the second vector minus the dot product of the first two vectors multiplied by the third vector. So in our case, we have omega crossed with omega crossed with r. And so this will be equal to omega dotted with r and then multiplied by omega minus omega dotted with omega multiplied by r. Now, if you'd like to try to figure this out on your own, I would encourage you to pause the video here. What you'll notice is that omega is in the k direction, and r is somewhere in the ij plane. So k and the ij plane are perpendicular to each other. So their dot product is 0. So this is equal to 0. And the dot product of omega dotted with omega is just omega squared. Because omega and omega, their vectors, are perfectly aligned. So you have k dotted with k. So this is just equal to minus omega squared r. So what we obtain is that the linear acceleration of any point on the rigid body is equal to the angular acceleration crossed with the position vector from the fixed axis to the point that we are looking at, minus omega squared multiplied by r. So what is this telling us? This is telling us that the linear acceleration can be decomposed into two perpendicular components. One of them is what we call the tangential acceleration, and the other one is the normal acceleration. So note that this here, we will call it the tangential acceleration, and this one here is called the normal acceleration. So AT is equal to alpha k crossed with r. And so this acts in the k crossed with r direction. And now the normal acceleration vector is equal to minus omega squared r. Now recall that r goes from the fixed axis to the point that we're looking at. Therefore, the normal acceleration points inwards towards the fixed axis in the negative r direction. So this acts in the negative r direction. So what we could say this is towards the axis of rotation. So let's draw this out. So we have our fixed coordinate system, x and y. We have a random object that is undergoing fixed axis rotation about this point O. So looking at point P here, if we call this point P, what do we have? We have a position vector going from O to P. But here I really want to draw the accelerations. So the accelerations, we have a normal acceleration here, an, which is equal to negative omega squared r. And we have a tangential acceleration, at, which is equal to the angular acceleration alpha crossed with the position vector r. And here we have our angular velocity and angular acceleration. So in this video, we've characterized mathematically 2 of the 3 modes of planar rigid body motion. In the next video, we're going to look at general planar motion and characterize its position, velocity, and acceleration at any point on the rigid body.